Assalamu alaikum, my dear students. I am Tahir Irfan, A-level chemistry teacher at Roots International College, A-level campus, Sialkot. Today we are going to understand Gibbs free energy change and its relationship with a chemical reaction. As you can see, this is the equation for Gibbs free energy change. Delta G, that is Gibbs free energy change, is equal to delta H. Delta H means the change in enthalpy. For a endothermic chemical reaction, this value is always positive, and for an exothermic chemical reaction, this value is negative. So delta H minus temperature, it must be Kelvin temperature. If the temperature is given in centigrade or Celsius, it must be changed into Kelvin by adding 273 into it and multiplied by change in entropy, that is the measure of the disorder in a particular system. For example, if a liquid is turning into gas, we can say its disorder increases, so delta S must be positive. Or alternatively, if a gas is changing into liquid, or 4 moles of gas are changing into 2 moles of gas in a particular chemical equation, so this value must be negative. So I have implanted this formula on Microsoft Excel sheet so that we can use different values to see whether a particular chemical reaction is feasible or not. Please remember, for a chemical reaction or a physical change to be feasible, this value delta G, the Gibbs free energy, must be negative. If this value is positive, that particular chemical reaction or physical change will not be feasible. So we take the first example in which delta H is negative and delta S, the change in entropy, is positive. For example, the change in entropy is 1000 and the reaction is taking place at 300 Kelvin, and the change in enthalpy is minus 50,000. So we can see the change in Gibbs free energy is minus 350,000 joule or minus 350 kilojoule. So because this value is negative, the reaction is easily feasible. An example of such chemical reaction is the burning, as you can see from this picture. Some fuel burning, petrol burning, gas burning, gasoline burning, natural gas burning, in which the heat is releasing out and the change in entropy is also positive. Look here, because the heat is given out, the enthalpy change is negative, and because some liquid is turning into gas, the entropy change is positive. So such chemical reactions are very feasible. Let's change some statistics. Suppose if I change the entropy, if I increase the entropy change to 2000, let's see what happens to this value. As you can see, it increase. So if change in entropy is more, the chemical reaction is more feasible, and if the change in entropy is lesser, for example it is only 200, the chemical reaction will be less feasible. Let's see the effect of changing the enthalpy change. As it is 50,000 kilojoule exothermic, I try to make it 100,000. As you can see, it is more feasible. Okay, let's check the third effect. Now the chemical reaction is taking place at 300 Kelvin and the change in Gibbs free energy is minus 160,000 joule or minus 160 kilojoule. I change this value to 400 Kelvin. The reaction is more feasible because this is the Gibbs free energy is more negative, and if I change this value to 200 Kelvin, so it is less feasible. So please remember, such type of chemical reactions are changed by changing these values, and they are very feasible because the first value is negative and the change in entropy is positive, as we can see. So this value is also gonna be negative, so negative added to negative, the final answer is gonna be negative. Okay students, a second case in which the change in enthalpy is positive but the change in entropy, that is also positive. The both values are positive. For example, I write the value 100,000 and the entropy change, that is 100, and the reaction is taking place at 400 Kelvin. So as you can see, so this Gibbs free energy change is positive. It means this particular chemical reaction will not be feasible. But if I increase these values, for example, I make it 1000, as you can see, the Gibbs free energy change becomes negative. Or if I use the same value but I increase the temperature here, so I can see this particular chemical reaction becomes feasible. So such chemical reaction in which the enthalpy change is positive and the change in entropy is also positive, they require these setting that either the temperature should be higher or the change in entropy should be more. So in that particular case, the reaction is feasible. As you can see, the example of such chemical reaction is thermal decomposition. For example, thermal decomposition of calcium carbonate into carbon dioxide and calcium oxide, or magnesium carbonate. So many carbonates, they are decomposed when they are heated. So in this particular scenario, as the Bunsen burner is giving heat to calcium carbonates, the enthalpy change is positive and there is an increase in entropy as the solid powder is changing into gas. So it means there is increase in entropy. So these type of thermal decomposition, they mostly require higher temperature, then they become feasible. Because if I make the temperature lower, for example 1000, so as you can see in this particular case this becomes 0, so it is not feasible. If I make it 1001, then it start becoming negative. Okay,